So let us start. At this lecture, we will consider the problem of equilibrium in composite thermodynamic systems. These are systems that include several subsystems, which are also thermodynamic systems. Let us write the name of the lecture, the title of the lecture, Principle of Maximum Entropy. Of entropy maximum. And entropy maximum. Okay. And let us start from explaining of the problem, and then we will proceed with mathematical formulation of the problem set. Let us first let me first recall that in thermodynamics, each system is determined by so-called fundamental relation, which connects internal energy, entropy, maybe volume, and maybe some other characteristics of the system. If we solve this relation with respect to the internal energy, we will find something like this. Here. And differentiating internal energy with respect to the extensive variables S, V, and other variables, we will get the equations of state. U is constant, and pressure P and maybe some other relations which I do not want to write out. And we told that this function, or the same, this function, are found from the experiment. This means that I need experiments, or maybe a series of experiments, to construct the thermodynamics of a given system. This approach has at least two problems. And let me maybe not two, but one very big problem. And let me explain what is the problem. When we make a series of experiments, we consider our thermodynamic system as some kind of black box that has some characteristics, let's say internal energy, entropy, volume, and some others. But we do not address a question: what is happening inside the system? When we make experiment, the thermodynamic system is some kind of box where something has happened, but we do not know what something is happening here. Let me be a little bit more concrete. Let me suggest that my system includes 3 reservoirs. Let me draw there is 3 reservoirs. And I suggest that they are connected by some pipes. And we have a piston inside each reservoir. Let me draw position of the piston here. And this, they may conduct heat or not conduct heat. This is not important. We can determine this fact later, but they can move in principle. Or maybe, okay, they can move. And here, and these reservoirs are filled with various substances. Here, we have gas 1. Here, we have a mixture of 2 gases which can transform to each other. So we follow a chemical reaction here. Gas 2 changes with gas 3. And here I have a vapor, a liquid, and a vapor. And here I have gas 4, this is a vapor, and a liquid 4. This is a very complicated system, and we follow the flow of the matter here. And I can make external pressure from here, or act with external force on this piston, or may not act by external force. Okay, and this is a system. From the viewpoint of the thermodynamical approach, we have 2 points of view on the system. If we say that it is a black box, it's a thermodynamic system with 2 degrees of freedom. Why 2? Because it must have thermal degrees of freedom, or maybe heat degrees of freedom, and it can change in size. So we have 2 independent characteristics, let's say entropy and volume, and making experiments on this system, we will find a fundamental relation that connects these 3 parameters. I'm going to say that this information may be insufficient in many cases. At first, it's insufficient because we do not control any changes inside these reservoirs. For example, when we increase the pressure, the external pressure on this piston, the volumes of the reservoirs here and here will necessarily change. And these changes cause change in the chemical composition here and change in the proportions of vapor and liquid here. This may be quite dangerous if we do not know what is happening here. For example, if we increase external pressure, the fraction of gas, say gas 3, increases, and if gas 3 is chemically active, we will get active chemical substance inside, and it can break our device. If we can look at this point, if we increase the pressure, the volume of vapor can be very, very small at some point. And this can decrease compressibility of the system. And this means following: if it's hard to compress liquid, we have to apply bigger force here. And this force can be very, very big. And again, we can damage our device. Finally, we see that the volume of our system, let's say a total volume, here, here, and here, filled volume with gas, a volume of gas here, and volume of these two reservoirs, is not arbitrary function. If I put it's not a good idea. Let me V prime 1, the volume of first reservoir, okay, let me write V1 max is a, no, okay, let me prime put here, and V3 prime as the volume of second reservoir and V3 of volume of third reservoir. We will observe that volume is in fact less or equal than V1 prime plus V2 prime plus V3 prime, and it's certainly bigger than V2 prime plus V3 prime. This inequality appears from the structure of our system. Our wall, our piston, can move only inside one reservoir. And when it goes down to the limit, there is no gas inside this reservoir. But this reservoir, this one and this one, are still filled with gas. If we don't know this limitation, we don't know when our piston will stop in his moving down. That's why we need to know limitations in which the parameters change. This problem setting, the explained example tells us that it's very important to study composite systems, the systems that include several subsystems. Of course, we have to suppose that these several subsystems has known properties. Another point is quite tricky, but let me focus on it too. When we write when we write this relation, this fundamental relation, we suggest that the piston, in fact, is a wall that divides the space with gas and the space without gas. That means it divides reservoir into two parts. One is filled with gas and the other is without gas. We do this automatically because we know that gas fills all the available volume. But in fact, it is a physical law. It agrees with our intuition, but it is a physical law. We almost never address the following question. Why it cannot happen that gas fills only part of the volume? Why gas fills all the volume, not a part of the reservoir? In principle, this imaginary situation is possible. This imaginary situation is possible, and this means that we have one more subsystem which is vacuum. And we know from the experiments that in the equilibrium state, gas fills all empty space. But this is a law. We have to prove it. And to make a proof of this fact, we can imagine that, in fact, this border is the border of piston, and we have a vacuum here and gas here. And the borders and the limits and the motion of piston is limited by the volume of reservoir. This means the following: if we forget about external pressure, this piston must reach its the position with the maximum available volume inside of the reservoir. And this law can be proved by means of thermodynamics. Okay, we started from very particular example, but let us formulate a more general problem which we will consider at the lecture. I do not want to erase this picture. It will be useful for us in future, but let me draw another picture. Suppose that we have a big thermodynamic system and it's composite. This means that it includes several subsystems. Let me label these subsystems by index I equals to 1, I equals to 2, I equals to 3, some here, I equals to n. The index I runs over integer numbers from 1 to n. And we choose the parameters that characterize our subsystems. We will say that we will denote entropy of the subsystem with number E as S sub Y, internal energy by U sub Y. Let me say that we have a volume, so I'll take VI, and some other parameters I will denote by X, Y, A. And A will run from 1 to, okay, from 2 to M. It's better to say 2 because V is x1. It's better to think that V I is x, y, 1y, 1I. Okay, and I suggest that all my systems are characterized, subsystems are characterized by one and the same set of parameters. So if we know how if M equals to 1, and all the systems have entropy, internal energy, and volume. And I suggest that I know the fundamental relations for the system. This means that I have taken a separate system 1, on system 1 some time, and then made an experiment and determined a relation between these parameters. This means that I know functions, let's say fi of si, ui, si, vi, and xi. I know that I know these ones. Okay. And this is what I know about the subsystems, about the subsystems. I also assume that my system has the same set of parameters as the subsystems. The characteristics, okay, the extensive characteristics of the big system, of a whole system, I will denote by S, U, V, X, Y, X, Y. And I know that these systems, these parameters are extensive. Not good idea. Okay, not good idea. So, the total energy of the system is a sum of internal energies of subsystems. The total volume is the sum of volumes of subsystems, and the same true for other characteristics. Okay, not E, not Y, here Y. Okay. For entropy, I think it's better to write here. Okay, let me write here. For entropy, we have the same expressions. Same expression. The entropy of a total system is the sum of entropies of subsystems. But this is not all. We have a fundamental relation for each subsystem. And this means that I can express entropy, and let me say that I can always do this as a function of other extensive parameters. Uy, Vy, x, y, a. some restriction that we have such representation, but let me say that it's okay. Let us postulate that it's okay. So I have the following representation for entropy. Vy, Vi, Z. Sometimes this function is called entropy function. And this is the entropy function for subsystem. U runs from 1 to n, I runs from 1 to n. And this is the entropy function for the whole system. Entropy function for the whole system. Okay. Okay. And please look at these expressions. Let's look at this expression. It tells us that the entropy of the system depends on the parameters of subsystems. Okay, this is very simple observation. This is very simple observation, and it's but this is not all. But this is not all. How to go it better? Okay. Okay. This representation for entropy will be our final result if we had a system that includes independent or maybe non-interacting subsystems. Okay, if we have walls here, and these walls, let's say fixed, so then each subsystem is just an independent thermodynamic system, is a closed thermodynamic system. It has an entropy and just total entropy of the system is just a sum of entropies of subsystem. Okay, but this is not interesting case, because at this example the subsystems are interact. They have various types of interaction. They have a mechanical contact. Here we have chemical transformations, and here we have transition between different phases. So this is not the end if we have a contact, because this is not the end, because the subsystems are interact. Let me formalize this statement by the following. Let me formalize this statement as follows. Okay. If our system has only if our system is closed. Let's okay. Let's formalize how to do this better. Okay, let us say that we have a closed system. And let us suggest that the big system is closed. Then we say that the total energy of the system is constant. Because the closed system has no thermal or mechanical or material contact with environment, so its internal energy is a constant. Closed. The same is true for volume. Okay. And the same is true for all other extensive characteristics. And again is constant. Okay. And this is true in all the thermodynamic, and this is absolutely true in all the cases. And now, if we consider, and now we have to discuss the interaction between subsystems, let's say. And this is true for all systems, for big system, and again we can say that we have no interaction between subsystems. Okay, no interaction. Then we will have a big system that includes several subsystems, and each of them is closed. So we have to say that all the parameters of the subsystems are also constants. And this is case is not interesting, because we know all about the system, and when we find the entropy function of the system here. Okay, but let me say that I will have interaction between the systems, between the subsystems. What will change? What will change if I have interaction between subsystems? Then, okay, then I can't use these rigid conditions. For example, if the subsystems can change the volume, maybe not all, but some of them, I can't say that volume is constant. If I have some other changes, let's say phase transformations, I can't say this one. And if I have a heat flow between the systems, I can say that internal energy is constant. In fact, if I have changes in my system, I have changes in my system, I have to say that I have some functions. Let's denote them f sub alpha, that tells us that can change, can take several values from, let's say, f alpha maximum, and here f alpha minimum. And let's say that alpha runs from 1, and these relations will express the types, all the possible types of interactions. All the possible types of interactions. Let me let me give an example. Let us go here at this picture. Let us go at this picture, and suppose that we fixed this piston and fixed this piston by the all motion here. And if the volume of this filled by gas, this mixture gas 2 and gas 3 is V2, and the volume is which is filled by mixture of gas and liquid V3, V2 is sum of here and here. I will have V2 plus V3, let's say, okay, not fixed. Okay. Let me. It's not good idea to fix here. Let us forget about fixing. I will have obvious restriction. V2 prime plus V3 prime. Unless this restriction tells us that this piston can go up, and in this case our subsystem filled 2 reservoirs. It can go down to the limit, and these 2 substances fill only 1 reservoir. This is an example. This is a particular example. The same restrictions I can impose on the parameters of the system at all, of the parameters of big system. Let me write them as f beta, let me write prime beta minimum u v x eta and as far as I know that the parameters of the system are sum of the parameters of extensive parameters of subsystem, we get the relations of the same type. So I can forget about these primes and say here R plus 1 S. And here, example, I told you, already gave you example. It concerns the total volume of this system. V is less than or equal than V1 prime plus V2 prime plus V3 prime plus V2 plus V3 prime. Okay, I think we should have 5 minutes break. If you have questions, you may ask them to me. And okay, and we considered a system that includes several subsystems and which has interaction. And we told that in the presence of interaction, the parameters of subsystems now can change. And this change, in some sense, can be considered as a thermodynamic process. And for example, if all the changes happen quasi-statically, this will mean that we have a quasi-statical thermodynamic process that changes the parameters inside the system. And this thermodynamic process is in fact relaxation. I mean, this is a relaxation because we have this is a relaxation if we have no external action on the system. If the system is closed, this process is a relaxation, and it will continue until some point. And when this process will stop, the positions of the walls will be slightly different than in the initial state. And this process and the presence of relaxation process tells us that now the positions of the walls, for example, the positions of these pistons, or the volume of liquid and vapor in this reservoir, are in fact not independent parameters, but they should be determined from the certain condition. And the presence of interaction means that such system has less independent parameters than the composite system with non-interacting subsystems. Again, let me look at this example. If we had no interaction between these reservoirs, we will say that we have 1, 2, 3 different subsystems, and each of them has its own characteristics and so on. When we allow interaction, we have only one macroscopic parameter that characterizes its size, its volume, and we also have entropy, 2 parameters, 2 degrees of freedom. And all these guys find their position from the requirement, from certain requirement. Okay, and we are interested in a rule that allows us to determine these positions. Let us introduce a terminology. Here, let us introduce a terminology, and let us say that relations of the form, this one, these are relations of one and the same nature, are called thermodynamic constraints. Thermodynamic constraints. And the thermodynamic constraints explain us how these systems are interacting. The example shows that the constraints can be two forms: restrictive at this such as f alpha minimum is equals f alpha maximum, and they imply an equation f alpha of ui si vi and say other equals to f alpha. Okay, let's say it could be f alpha minimum and the same is alpha maximum. We have in a closed system, we have only one restrictive constraint in absolutely all the cases. In the closed system, this is a law of conservation of energy. This constraint always exists, and it's always restricted, because the value of energy in a closed system in each possible state equals to the internal value of internal energy, to the initial value of internal energy. And the constraints may be, and when we add other restrictive constraints, we say in fact that some rules cannot move. Let's say if we say that V is constant, we say that one subsystem do not change its volume. And let me stress that the restrictive constraint decreases the number of independent parameters in our system. Okay, from this I can express, let's say, U1 as a function of other energies. Internal energy of first system, like as the internal energy in terms of internal energy of other subsystems. And the constraints can be non-restrictive if f alpha max. The examples of non-restrictive constraints are here. And non-restrictive constraints appear if we have interaction between subsystems, and they explain us how the interaction happens. For example, this constraint tells us that this piston has limits of motion, and this one tells that this piston has its limits of motion. And please note that non-restrictive or maybe restrictive constraints can be applied to the parameters of subsystems and to the parameters of the whole system. But it's the same, as I already explained, that the total volume of the system is in fact a sum of volumes of subsystems. The principle of entropy maximum tells us the following. It tells that entropy of total system tends to maximum in the presence of constants, of constraints. What this means? Okay, in the state of equilibrium. Okay. What this principle says? It tells us that we can determine the equilibrium state of the system, maximizing this function in the presence of constraints. If the constraints are rigid, this is just some algebraical equations, and we have a conditional extremum problem. And if these constraints are non-restrictive, we see for extremum of entropy of this function, this entropy function, at the subset of states that satisfy thermodynamic constraints. Let me recall the principle: entropy of the system reaches maximum in the presence of constraints in the state of equilibrium. And this principle reduces the problem of determination of equilibrium state of the system to the problem of conditional extremum for certain function, for the entropy function. And when we find the conditional extremum, we will determine equilibrium, the values of, let's say, internal parameters, the parameters of the subsystems in the state of equilibrium. Okay, and this principle explains how to describe a state of composite system if we know the thermodynamics of each subsystem. Let me demonstrate the work of the principle in several examples. And let me start from example 1. And here I want to prove well-known statement that gas fills all the available volume. Okay, that gas fills all the available volume. What is my system? My system is a reservoir, and it's covered by some wall, by some piston which can move up and down. To be concrete, I consider ideal gas, and I think that I have no chemical transformations. This means that I can say that I have 1 mole of the gas inside my reservoir. The entropy function of the ideal gas. Okay, let's find the entropy function of ideal gas. We know the entropy of the ideal gas with constant heat capacity. Okay, it's very easy to calculate this fact, very easy, and we have already done this at the lectures. For example, for example, ds, we have a very simple representation, ds over dt. ds over dt for constant V equals to heat capacity divided by T, and I assume that my heat capacity is constant, and here ds divided by V for constant T. It's quite difficult for constant T. It's quite difficult to compute, but we can express this. Should be something like it's very easy to compute this derivative if we know fact that U equals CVT. Let us think that we know that fact. Then we have then the thermodynamic identity says here, if I put and U constant, and if I put T equals constant, this means that U is constant. This is important here. And then du equals to 0. So I get relation TTS minus PdV equals 0. And from here, I have ratio of differentials ds over dv equals p. Okay, let me 1 second. P equals divided by t. And here I know the equation of state. Here. And this is for u constant. And this is derivative of what I'm interested in. And from the equation of state, P divided by T equals V R divided by V. So, and integrating, we know here derivatives, integrating, and here we get some constant x0. Okay, this is entropy function. Not entropy function. And to get entropy function, I should express U in terms of temperature, in terms of internal energy and heat capacity. Okay, and this is entropy function. We have two constraints. We have to say that our system is closed. Because when we say that gas fills all the volume, all the available volume, we know that no external forces act on the gas. This is the first reason. The second reason I forget, and is to say that principle of maximum of entropy works for closed systems. This is important. Please note that it works for closed system. So here it's very important that it works for closed systems. Okay, so we have a constraint, U is constant. And what will be other constraint for our system? If this piston is fixed, then I say that V equals, let's say, V0. And this is a restrictive constraint. But we are interested, but it's not interesting case for us. We want to show that gas fills all the available volume. So I had to say that piston is moving, and its limitation to the maximum, it corresponds to the maximum possible position, upper position of the piston. And here I can put 0. In fact, this is not good idea to put 0, because in zero volume we have infinite pressure. So I have to say that the piston can go down up to certain lowest position, and I will say that is minimum by minimum. The minimum is the volume which corresponds to the minimum lowest position of the piston. And the principle of maximum entropy tells us that the parameters of the system, that in the equilibrium state, the parameters of the system deliver the maximum possible value of entropy. So we should find the maximum value of entropy in the presence of these two relations, in the presence of these two constraints. Okay, the answer is immediate because U is constant and entropy is monotonously increasing function of the volume. The bigger volume, the bigger is entropy. Hence, the entropy is maximal for V equals to the V maximum. Because U is constant and ds by dv for constant U is P over T and it's greater than 0. Okay, this example tells us that if we leave a reservoir with gas closed with piston and this piston can move, after some time we will find that the piston goes into its opposite position, to the position that delivers maximum volume for the gas inside. Okay, this is true. This can be observed in experiment and so on. Okay, let us consider another example. Let's consider another example. And I forgot to say a very important thing. Okay, but I will say it now. Let me write example 2 and suggest that we have a mixture of gases. And let us consider the case when we have a mixture of ideal gases. This means that we have several different types, let's say, of atoms, maybe of molecules, that inside my reservoir, and okay, mixture of ideal gases, and I do not follow chemical reactions, so the amount of substance of each type is constant, and but I do not say that it's constant at all, and I'm going to find the equilibrium state in the contact with heat reservoir, which has T equals with the temperature Tr. In fact, this is very often, this problem setting appears very often in many applications. So let's say we have air in some balloon maybe, or in some bottle or in some reservoir. It could be under the pressure. And if our reservoir has a thermal contact with atmosphere, we have a contact with heat reservoir. And here we have also and here we have a problem of determination of equilibrium state of open system. And very important, please note that the system is open because it has a thermal contact with heat reservoir. But we know how we can deal with this problem. If the system is open, in the closed system, entropy reaches maximum. But if the system is open and it has a thermal contact with heat reservoir, we know that the free energy of the system has to be 10 to maximum for temperature equals to the temperature of reservoir, and this is a result of previous lecture, and plus we have to account constraints. So let me correct here what we should have. Open and thermal contact. With reservoir. With temperature 10 equals 10. So we should consider not entropy but free energy. Let us again note that this is a result of previous lecture, and it should tend to minimum with account of constraints, and here it's important we should put that the temperature equals to the temperature of reservoir. This is very important, and this is a consequence of thermal contact. Okay, and this is for contact for system with thermal reservoir, with the heat reservoir, and for reservoir of work and so on, we will have here not free energy but other potentials. So it's again as a result of previous lecture. Okay, we know the free energy of gas very well. If we have only one component of gas, let's say the index y labels the components of gas. We have the free energy of component minus n minus ni ti cv. Here heat capacity of 1 mole again, molar heat capacity ln ty minus r divided logarithm vy divided by n sub y. Okay, and plus s sub 0 y, so this is y0. It's some constant that related to the initial value of entropy, and plus n I u I 0. And this is initial value of internal energy. Okay, let me leave this one. It does not matter for this application, but later it can be very important. This is some kind of internal energy at 0 temperature. Okay, for the total the total free energy is just the sum of free energies of the system. And here should be big sum. Okay. And this function should be tend to minimum for temperature equals to the temperature reservoir. We have several components and all of them must have one of the same temperature. Okay, and we have several constraints. As the system is open, we can say that energy conserves, but we have a restriction on the volume. V sub I less than V maximum and bigger than V minimum. This constraint says that in principle it is possible a very imaginary situation when, say, gas 1 fills only part of my reservoir while other part is empty. Okay, we know that this is not true. So okay, I put here temperature equal to the temperature of reservoir here, and tend this function to minimum. I see that this is monotonously decreasing function of volume, because I can differentiate by volume here, and I see that V equals to V max at F равно F minimum, at the minimum of F. This tells us that all the gases, all the components in the ideal gas fill all the volume of the reservoir, and this also tells us that all the gases have one and the same temperature. Let me write out the final result. Here I forgot about that Tr equals to Ti. I omit R, so I replace Tr just by T, and I write out the free energy of the mixture of gases. Okay, I here made a misprint. Let's put I here. In principle, the gases have different heat capacity. Okay, logarithm of T minus R. And here I write not VI, but the volume of reservoir. It's a universal value for all the cases. Here, put here as Ny U E 0. Please. please outline this formula. Please take this formula into the box. We will use it in 2 lectures. And here I want to demonstrate one very simple consequence of the result of our representation for free energy. So-called Dalton's law. Okay. Let us consider the pressure of gas. By the definition, P equals dF by dV for T, E and N is constant. Okay. And this is universal definition. And now we can compute the pressure of mixture of gases. Counting that F equals to the free energy equals to the sum of free energies. And accounting that the volume is one the same for all the gases, we find P equals to minus sum over N dFi over dV Tn, and I take minus here, and in fact this is a pressure of gas I in the absence of all other gases. Look, if I take a single gas I will have the free energy of such form, and differentiating this free energy with respect to volume, I get the pressure of gas in absence of all other gases. And here the sum. This law, and this is a Dalton's law. It tells us that the pressure of gases, of mixture of gases, equals to the sum of pressures of components of this mixture in absence of all other gases. For example, if we want to compute the pressure of air, we believe that air is an ideal gas, we may divide air into components, let's say oxygen, nitrogen, maybe some noble gases and so on. And if we put only nitrogen in the reservoir, then we put oxygen into reservoir and measure the pressure again, put noble gases separately, each noble gas, maybe carbon dioxide and so on, and if we measure all the pressures of all the components in our reservoir separately, and then take the sum, we will get the pressure of the air in this reservoir. Of course, this is true only if we believe that air is an ideal gas. In case of non-ideal gases, the problem is slightly more complicated. I think we can finish. If you have questions, you may ask them to me.